I think I have the pleasure of introducing the next speaker. Next speaker is Dorian Amiet. He's a long-term collaborator of Securosys. He has been with us maybe 8-9 years ago. He now is a senior researcher at the University of Applied Science of Eastern Switzerland, and we are still collaborating. And Dorian is doing his research on side channel resilience and also side channel resilience of those post-quantum algorithms. So Dorian, I'm happy to have you here. The stage is yours.
Okay, thank you, Marcel. We worked together quite a long, and Securosys was actually very early in the post-quantum thematics. I skip why they do it, because we hear it today a lot. What I want to dig is into one single algorithm and looking into details. So I try to explain you how the Sphinx verse or the FIPS 205 or the SLH-DSA. So it is hash-based, which means it's super cool because everybody agrees, or most people agree, that hash will not be broken soon. And if you make a signing system that only depends on the security of hash, you're actually pretty good because you need the hashes anyway to sign something. So we have now a hash function H and a message. We say we take any random number, which is this X, and this is our private key. Then we can take the hash of this number, or we can take the hash again of these numbers and the hash again, and then this way we make a chain. This all gives us 4 numbers, and we have a private key. Down here we have a public key up here. So this is what we published, the top one. And if we have a message, we say, okay, let's take 2 bits of this message. If it's a 0, we release actually our private key. If it's a 1-1, we can take the public key. If it's in the pin, we take the corresponding device. We have to do this many times to get a full message, because signing 2 bits is a bit nonsense, but if we do this 128 times, you already have 256 bits. Then a full private key, signature, and the public key more or less looks like this. What we have in the end is something like a checksum to get, that makes it impossible to sign a message which has like an all-one message. Because I can say, okay, I see your signature, I can easily sign all-one message. So this is why we add some few more bits, where we have a checksum that ensures that if a single bit changes in my message, I have at least 1 node missing, so that I cannot generate another signature. And this is called the one-time signature. So we already have our signature hash-based. It's just pretty useless because you can use it once. If you use it more than once, you're already broken. And this would be very fast, small, and cool, but only usable once. So then we can say, okay, instead of having just a single signature, I can say, okay, let's take a few of these single signatures and put them together in a shared public key. Now I have here my private keys, the public key of the single signature, then I hash the public key and I hash these together. So I take a second private key, it has a corresponding public key, hash it, and then hash everything together until I get up here and say, okay, now this is my public key. And if I sign something, I have to pick one of my private keys. In this example, I took this one here. And then I have to give to the signature, of course. This is my signature, but I also add this node and this node as extra numbers so that if someone wants to verify the number, then he can calculate this number, this number, this number, and this number, so that, and if that one matches with my public key, which is actually this number, then I know, okay, the one who signed that knows my X2. This is already a system that's in use. This is the XMSS. It generally works. We can do a fuse signature, or just like the number as big as the tree is. The problem is it's very hard to remain, okay, I used X0, I used X1, I used X2, I can now only use X3, and this can be hard to track in system. Imagine if you want it on parallel systems which don't know something from each other, or if something crashes and you reboot, you have to ensure that your checklists which are taken are still there. And this is called the stateful hash-based signature. So, but what we want is stateless, meaning that we can we don't need to remember which one we used. And for that, I have to give you a third thing, and this is a few-time signature. From a conceptual view, it's pretty similar to the one-time signature, but you make a lot of security margin so that if you make two signatures with the same, you still have enough security. If you have 3, it's probably still enough. If you have 4, it's probably still enough, but it will at some point decline. But the idea is, instead of this change, I take multiple trees. These are all private nodes here, the red ones. This part here, signs, if it's 2 to the power of 10, is the size of these trees, the base number, so it's 2024. Then it signs me 10 message bits. And all I do is, if I have here, if my message is represented as an integer number, it's a number 5, then I say, okay, I release only that part here. And then again, it's the same. So my signature is then my private key part, which is here. And I need to give the verifier all these nodes that he can calculate the top for itself. This I do multiple times. I take the message even a bit longer than my 256-bit so that I get security margin, because that way it's still hard. If I have, let's say, I picked it twice, I have 2 signatures, I have then this released and maybe this one. It's still hard to get hash value which contains only numbers that I already have released. And this is more or less the idea of this few-time signature. Still hash-based. And we can use our key a few times. And now if we mix both together, we can generate our stateless practical hash-based, incredible, nice cryptographic signature, which was called Sphinx during the NIST competition and is now in FIPS 205 or the SLH-DSA. You have seen all the names already in the talk before, but this is more or less what it is. We have our few-time signature at the bottom. If we now want to sign something, I pick my start point in my big tree of one-time signatures. I have maybe 2 to the power of 60 options, so I pick one at random. Then I take my my few-time signature, which gets a key, and this key is then verified with one of my one-time signature, again in the tree of signatures, and this replies in multiple trees so that I can build my tree big. Why do I split it in multiple trees? It's very easy. If I have a tree size in total of 2 to the power of 60, then I would have to calculate all public values so that I can generate my green nodes. And this is why we split it into 4 smaller trees, maybe 2 to the power of 8 or so, 256, which is still doable. And as you already saw, or maybe see, it's that you really need to calculate a lot of hash functions to just generate a single hash, and generate a single signature. On the pro side, the verification is pretty fast because you just have to do this few hash calculations to make the verification. It has a few variants, but I think I will skip that. So as we worked with Securosys, they don't want a system that takes you a second to generate a signature. So we said, okay, they already have an FPGA, so meaning hardware, and we can build our specialized core in there. So this is what we came up with. We have a big core that just can calculate terabits per second of hash input and output. And all around it is just built so that I can build up my trees of trees. It was pretty fast. So this is the orange one, is a CPU. The numbers are from the NIST contest back then, so the hardware of the FPGA and the CPU is more or less the same age, so I think it's more or less fair. And we reached about a factor of 60. There was also a special version of Haraka within the contest where they had AAS as the hash function, or a form of AAS, where they had the hardware accelerator on the CPU, and this was more or less in the middle in the logarithmic scale. So we have like a factor of 8 compared to the hardware accelerated CPU, and another factor of 8 of just a plain CPU implementation. When the CPUs came up with shake inside hardware accelerated, it will come down. Long story short, we reached around a millisecond for signing time, which is pretty cool, I would say. So it's because I think this is the main drawback. But it has a second one, and this is if you have local access to your hardware. Here we built a platform just to measure how much power it uses. We can measure magnetic fields, and we have all the supplies that are used for the chip external, so that we can also play with this one. And the Sphinx Plus, or the hash-based security, is really good against, let's say, just power attacks. So if I take a trace of, I look at the voltage that or at the current it takes during the calculation of a single signature, then it's really robust, and it's probably hard to make something wrong there, because everything that is really private goes only into the hash function, and there are always many bits processed at the same time. It makes it hard as an attacker. But you can, as I already said, we can also play with the supply voltage, and with that, like a glitch like this, so it should have like 1 volt, and if we drop it for a short time, we may provoke an error during the processing so that it calculates something wrong. But we don't go that far that it turns off, because then we don't win anything. Then we just have a broken or a off system. And if we get such a calculation error, let's say here, during let's say this is the last one-time signature tree. So this is actually our public key. This is the last verification of the public key below. Our signature was here. That one, we don't make a fault. But we need to calculate this node. What do we have to calculate for that? We calculate this public key from the one-time signature here and the public key here. And let's say I put in such a fault in here, which is actually doesn't need to be that precision in time, because it would also work if it was that one here. But then the public key here will have like 50% changed bits. That means that node here has also 50% changes bit, that one as well, and the root here as well. And this was the part of this was the public key that gets verified with this. In normal operation, this will always be exactly the same value, and I can use my one-time signature. This is our original without faults. I can come through this 1,000 times. I don't release anything because this would always be the same value bit by bit. So the signature is always the same. But now with the fault, I will assign a different root and release some of my privates here. So here, I didn't want anything because I already knew that one here. But here I had a 0, which means releasing the part of the private key. Here I don't get anything and stuff like this. And here, if I just get a single one, I already won because I said this is a one-time signature. But now, if you forward it and if you track the output, you get 2 different outputs of a one-time signature, which is already enough. To release like the full private key, you take it. I mean, this is a statistical event, and you need some 50, 60 tries. But it's, I mean, this is absolutely doing. If you can take 10 per second, it's 5 seconds, and you're done. And then there is one thing. Usually, a fault attack is visible if you then verify. Say, okay, I said, haha, verification is fast, so I can say, just verify your signature. But unfortunately, this is not enough because the error was here, which means this is all wrong. But as the signature here is also different, the signature is actually valid, which makes it hard to detect because you cannot say, okay, sign verify and I'm good, because it will be a true signature. And the only thing you can do is somehow double it, so calculate twice, because it's hard to provoke the same fault twice. This you can detect, or maybe do an extra hardware to detect such faults. Okay, I think this is it. We made a fast FPGA implementation, and we saw that this glitch attack is really tricky and can be performed from some experienced engineers. Thank you.
Thank you, Dorian. Yeah, I think that was a rather very technical and highly interesting, but the talk. So I think, if I understood you correctly, what we have seen is that with glitching, we have a very high attack potential on hash-based signatures.
That's true.
Is that the message? Okay. Now, of course, Tim said you use SLH signatures, SLH-DSA signatures in certain cases when you want to be very sure. So do we know something about the side channel attacks on ML-DSA? Or no, sorry, on ML-Chem.
So in general, I would say it's probably all the standards do have the potential to be attacked through side channels. But one has to remember side channel attacks, especially this one, needs actual physical access, which is in a HSM, I don't think you will get to the FPGA supply without being detected by any circuit inside there. So you're already quite safe, or you can put it in the server room and just close the door, which may already help a lot. And then, I mean, this was now an active attack, meaning you actually need to provoke faults. It doesn't need to be a glitch on a vault. It can also be a EMP or so. And others, like the CAM, the key exchange. I think I had a talk last year here, where I presented an attack which is actually passive, meaning measuring the power, and that one works on the key exchange, the ML-Chem, during the encoding of the message, where you can just have a look at the power, and if you catch it, the signal, then you can calculate the message which was transferred, which is actually the key that is to be used later. Here I have a stand where I show RSA. So side channel is nothing new. I mean, RSA is very prone to this. Euclid curve are very prone to this. That one here, hash-based, is pretty good against these passive ones, which are usually more, as I would say, they are more used and have more the potential to be done from remote. Because imagine an FPGA in a data center that has shared logic. On one part of the logic from another customer, there is a crypto running, let's say RSA. And another core, you can actually generate cores that measures the supply voltage through the timing of the gates. And then you can make an attack from inside this FPGA if it has shared logic. This is very hypothetical, but it has been used.
Thank you, Dorian.